Okay, so let's look at the next way that we can dissolve a sparingly soluble compound. We can use a Lewis base that is able to form a complex ion with one of the cation species. So just as with the addition of a strong acid, right, we have multiple equilibrium steps here. So we're going to look at the same example with zinc hydroxide. And we have this KSP that's really, really small. So this gives us an idea of just how insoluble this compound is, right? And by insoluble, I don't mean definitively it won't dissolve, just how hard it is for it to dissolve, right? Based on this small KSP. Now, if we couple it with a complex formation reaction by adding ammonia, ammonia will essentially react away these zinc ions. So with the strong acid, we saw it react away the hydroxide ions. In this case, adding ammonia is going to react away the zinc ions to form this complex. And the reason that it does this, right, if you look at the KF, right, the equilibrium constant of formation, it's a really, really large value. So this reaction is highly favorable. So as a result of reacting away these zinc ions, this increases, right, shifts the reaction to the right, increasing the solubility of the zinc hydroxide. So here's our overall reaction when we add these two equilibria together. We have zinc hydroxide reacting with ammonia to form this complex ion with zinc as the central atom and ammonia ligands. And we're also releasing hydroxide ions. So take a moment to pause this video and calculate the overall equilibrium constant K. We're bringing it back. We're bringing it all together, right? What's the overall equilibrium constant K? Pause. All right. Welcome back. Welcome back. So to get the overall equilibrium constant K, if we're adding two reactions together, right? One of our rules, there were three rules that we talked about with coupled equilibrium and how we find the overall equilibrium constant K. We're going to multiply the equilibrium constant for each individual equilibrium step. So we do KSP times KF and we get 1.44 times 10 to the minus 8. Now, compare this value to the KSP for the dissolution reaction. What do you notice? Right? So quantitatively, we notice that the value is much larger. We went from a magnitude of 10 to the minus 17 to 10 to the minus 8. So that's what we notice quantitatively. What this means is by coupling this reaction to a complex formation, we increased the solubility of zinc hydroxide. We increase the solubility of zinc hydroxide. So we're going to pause here and then we're going to conclude in our next video with a actual realistic, I won't say realistic because it's not like these aren't realistic, but what I mean is an application to the environment. So we're going to look at coupled equilibria in the ocean. Dun dun dun.